Yeah, so thank you all for coming out today, particularly under the circumstances.
If you can explain all this, I'll speak to the Pope for you.
I'll see what I can do. Yeah, so this talk is part of a series of talks called How We Know What We Know. The previous talks in the series are about the history of science and the experiments and processes, thought processes that led to our current scientific understanding and knowledge base. This one is going to be a little bit different because the last talk was about the history of quantum mechanics, and I discovered during that talk that there were quite a number of people who, to my surprise, had never heard of quantum mechanics. I didn't think that was possible in today's world, but apparently it is. So I'm going to take a digression here and just talk about quantum mechanics rather than the history. One of the principal motivations for giving this series is to drive home the idea that science is different from other worldviews in that it does not ask you to take anybody's word for anything. It's based on experiments, many of which you can actually do yourself. And I encourage people, that some of these experiments in quantum mechanics sounds very esoteric, but they're actually experiments in quantum mechanics that you actually can do yourself. I was intending to do some of those for you, but unfortunately my old feeble brain left some of my props at home. I had some very large sheets of Polaroid film that would show up on camera that are still sitting on my desk. I have some little ones that I carry around on my wall. So I actually can show you these things, but they won't show up very well on camera. And you probably won't even be able to see them very well in the audience. But afterwards, come up close up and I'll show these to you. I do encourage you to try these things at home. You can do them with laser pointers and pencil leads. The equipment is very easily accessible nowadays. And I really do encourage people to really do these experiments and verify for yourself that the things that I'm telling you are true, because some of what I'm about to tell you is going to sound pretty incredible. So today's scientific knowledge rests on a foundation of two basic theories, one of which is quantum mechanics, the other of which is general relativity. General relativity is a theory of gravity. It's a theory of the very large, things that are in the size of planets and stars and galaxies and black holes and things like that. Quantum mechanics is a theory of the very small, atoms and the things that make up atoms, and also light. Arguably, the single biggest challenge in science right now is trying to reconcile these two theories because they are in some ways fundamentally at odds with each other. And this is one of the biggest mysteries in science. Nobody's been able to figure out how to reconcile the kind of worldview that quantum mechanics presents with the kind of worldview that general relativity presents. If you can figure it out, a Nobel Prize awaits you. So science right now is in this very weird situation where all of our knowledge rests on these two theories, and we know that at least one of them has to be wrong. But we don't know which one. They could both be wrong, and we're still trying to figure that out. By the end of this talk, you're probably going to think that quantum mechanics is the one that's wrong because it's just going to sound so bizarre. But it's actually the theory that's better supported by the data. So there actually are some experiments that have been done that are at odds with the predictions made by general relativity, and that's why you hear people talking about dark matter and dark energy, which are really just code words for the weird things that we don't understand that cause these experimental anomalies. Quantum mechanics, no experiment has ever been done that is at odds, whose results are at odds with the predictions made by quantum mechanics. It is the single best confirmed theory in the history of science. But I do have to warn you that, why is this not working? It's weird. So, in fact, it's so weird that Richard Feynman once famously said that no one understands quantum mechanics, or if you think you understand quantum mechanics, then you don't really understand quantum mechanics. I don't think the situation is quite that dire. I think that our understanding of quantum mechanics today is much better than it was in 1964 when Feynman said this. But it's really weird, so brace yourselves. The other thing that I feel the need to warn you about is that we're going to have to do some math. So I presume everybody's comfortable with this? No? Okay. This actually, I actually did pull this out of a paper on quantum mechanics. How about this? Everybody okay? So this is actually the fundamental equation of quantum mechanics. Obviously, I don't expect you to understand this, but trust me, by the end of the talk, you'll actually have a pretty good grip on what all these weird, squiggly Greek symbols mean. It's not as bad as you think. So we're not going to start here. We're going to start here.
That's good.
Everyone okay with that? Yeah. So obviously, everybody's comfortable with this. But if you think about the reason why you're comfortable with this has nothing to do with anything that's inherent about what's on the screen. What's on the screen here is well, it would be, if we were old school, it would be some ink on paper. Nowadays, it's some parts of the screen that are producing light and some parts of the screen that are not producing light that your eyes perceive in certain ways and interpret in certain ways because you've been trained from a very young age to see black shapes like this and attach some meaning to them. And unless you're a physicist, you have not been trained to attach meaning to black squiggles that have this shape. But fundamentally, what's going on here is really the same. There are some black squiggles that humans have invented that have some relationship to something physical that happens in the world. And these particular black squiggles have to do with describing the behavior of things, mundane things in the world. We invented those squiggles to count things like sheep and goats. But I'm going to use beach balls as a metaphor because they're more fun and colorful. So what those squiggles mean is that if you have a beach ball and you have another beach ball and you put them together and you want to describe the situation that results, you write down something like this, right? So these are black squiggles that have some relationship to something physical that's going on in the world, but the relationship between the squiggles and the physical thing that they describe, there's nothing about the squiggles that looks like beach balls. Right? They're completely arbitrary. They're just arbitrary shapes. It just so happens that with numbers, there's only one number system. With human languages, there are lots of different alphabets and stuff. We happen to have one universal number system that all humans use, but the shapes are still every bit as arbitrary as the shapes in an alphabet. And the mapping onto physical reality is a convention and something you've been trained for. This particular convention is something you've been trained for from a very early age, and it has to do with beach balls that you have some physical experience with. But there are other kinds of physical things that happen in the world that these kinds of black squiggles don't describe quite as well. So for example, if instead of beach balls, let's talk about piles of sand. So imagine you're a kid playing on the beach, and you make yourself a little pile of sand, and you want to know what happens if you have one pile of sand and another pile of sand, and you put those together the way you put the beach balls together. Well, what you end up with there is one bigger pile of sand, which is a different kind of physical phenomenon than what happens when you put beach balls together, right? And so to describe this physical situation, we might want to invent a different notation, like maybe that, right? To distinguish the behavior of piles of sand from the behavior of beach balls. And piles of sand also have this interesting other property that you can have holes, right? So you can have like a negative pile of sand that's a hole, and you can add a pile of sand to a hole or a negative pile of sand and end up with, well, nothing. And so we might invent some black squiggles to describe that physical situation. So the black squiggles that I showed you at the beginning that look so intimidating are describing a very, I don't want to say simple, but a commonplace physical situation. The physical situation that they're describing is waves. We've all seen waves on water. And it turns out that waves can be described mathematically. So what this is an animation of taking the mathematical description of a wave and animating it using a computer. So what's happening here is that imagine that you've dropped a rock into some water, and the rock falls in the water and it makes kind of a hole in the water as it goes in. And then what happens after that is that you get this splash and waves go out and they kind of peter out. I'm going to show you, if you look very closely at the very beginning, I'm going to click on this 3, 2, 1 now. You see that big spike in the middle? That's something that when I first wrote the code that produces this animation, I thought I'd made a mistake, because the first frame, this is the first frame in that animation, and it shows the rock has just fallen in. Imagine there's a rock here that you've thrown into the water. The very next frame, going by the math, it looks more or less the same. It has this big spike in the middle. That's got to be wrong. There has to be a bug in my code. But in fact, it's not. That's actually what happens. If you look at a photograph that's taken immediately after the rock goes in, there's this big spike. And so the math actually, if you trust the math, it makes predictions about the world that turn out to be correct. So what the math says about waves, this is the black squiggles that physicists use to describe waves. I'm going to tell you just a little bit about what this means, just to make it a little bit less intimidating. This black squiggle with the 2 above it, all this means is the rate of change and the rate of change of something. So this is a Greek letter delta, lowercase Greek letter delta. So these deltas mean the rate of change, and the 2 means you do the rate of change twice. So this is like an acceleration in something with respect to time is equal to some constant times the acceleration with respect to space. So don't worry about the details. The point is that these black squiggles have something to do with the rate of change, the rates of changes of things. And when you crunch the numbers on this, the way you crunch regular numbers, what you end up with is a description of things that move in circles. And it turns out that things that move in circles in particular ways produce waves. And the best way to illustrate that is just to show you. So if you look at the top, you'll see a wave moving from left to right. And the row underneath it, you'll see exactly the same thing, except that if you follow one of those dots, what you'll see is that every single one of those dots is just moving in a circle. Can everybody see that? Does anybody not see that? Because this is going to be really, really important. It's kind of mesmerizing, isn't it?
I could for hours.
Yeah. When I first saw this, I thought, wow, that is really cool. So quantum mechanics has to do with this. The math has to do with describing waves, which has to do with describing circles. And that equation that I showed you at the beginning, the one that describes these waves, that describes these circles, is called Schrodinger's equation, after the guy who discovered or invented it, depending on your perspective. It has a very important property called linearity. So it's a linear equation. And what that means is that if you have two solutions to that equation and you add them together, the sum of those two solutions is also guaranteed to be a solution. And what that means is that in order to solve that equation, you only have to find a couple of solutions, and then you can generate an infinite number of new solutions just by adding them together. And that is, in fact, the business of quantum mechanics. That's how you do quantum mechanics, is you find a couple of these core solutions, and then you add them together in different ways. And that process turns out to describe everything in the world that isn't the size of a planet, believe it or not. So I'm going to tell you a little bit about how you add waves. And the way that you add waves is that you add these circles. And so if you imagine that you have one thing moving in a red circle, another thing moving in a blue circle, you had to imagine, I forgot to draw these, the dots that were moving are at the end of these arrows. Because the way you add these things is you draw an arrow from the center of the circle out to where the dot is, and then you stick one arrow at the end of one arrow at the beginning of another, and you draw a new arrow from the end of the first arrow to the end of the second one, and that's how you add these circles, by adding arrows. And this also has some black squiggles that go along with it. This is the mathematical notation that there's different ways of writing this depending on exactly what it is that you want to do with these, but these are the intimidating looking symbols that you'll see in papers. This is all it means, is you're adding arrows that are moving around in circles. And there are, let's see, there are different ways. This is just another example that shows that the arrow that you get by adding two of these arrows can be shorter than either one of the ones that go into making it. I'm going to show you a couple of examples of this in animated form. So, oh, you know what? That was supposed to be animated. Hold on. Why is this not animating? Okay, I don't know why it's not. So, that was... I'm having all kinds of technical difficulties today. These were supposed to be moving around, and the result was a black arrow moving around in its own circle. The next one is, wow. Huh. We are experiencing technical difficulties. Okay. I'm going to have to go to a backup plan here. Oh.
Isn't that nice? He has problems.
Yep. This is very strange. I don't know. This actually happened to me earlier. I don't know why. Something is wrong with my computer, but I'm going to go to plan B here.
It's a failure of the quantum mechanics.
Okay, so this should work. This worked earlier. All right. So here you have two arrows moving around in a circle, and if you look at what's going on over here, this red arrow, I'll try to replay that for you. This red arrow is always going to be the same size and pointing in the same direction as this red arrow, and this blue arrow is always going to be the same size and direction as that blue arrow, and when they move around, what you end up with is, in this particular case, an ellipse. So here is another example. I hope this is another example. Why? No, that's the same one as before. Ah. So here's one where you have two circles. The result isn't necessarily a circle. It can be a line. And the interesting thing to notice about this one is that there are times when it goes through the center here when the sum of adding these two circles or waves together is 0. That's a phenomenon called destructive interference. And if I brought my props, I could actually demonstrate it to you with a laser pointer and some pencil leads. But I didn't, so I can't. But the point is that you can add two arrows that are pointing in opposite directions and they cancel each other out in exactly the same way that a pile of sand and a hole can cancel each other out and leave nothing. Boy. These things can combine in very interesting and complicated ways. Now, the shape that's going to end up here kind of sort of is going to remind you of some of the depictions of atoms with electrons whirling around. That is not what this is intended to evoke. These arrows are purely mathematical abstractions. They don't describe anything that's actually pointing in some direction in the real world, with a couple of, except in a couple of very special cases. But in general, it's just a purely abstract mathematical thing, and the drawings are here just to show you that what the complicated math is describing is conceptually very simple. This is the kind of thing that you can get from adding two of these circles. In real life, to get the kinds of situations that we deal with in everyday life, you're adding about 10 to the 23rd power, a number with 23 zeros after it. That number of different circles are all being added together, and they're moving around about the same, several trillion times a second. So that there's a huge, vast gap of complexity between the simple situations that I'm showing you here and the real world, but conceptually it's all exactly the same. It's all just adding up things moving in circles. So I think, oh, I got one more. Oh yeah, so this is one that just shows how you can, in a way that's easier to see, how you can get two of these that add up to nothing. All right. So I'm going to go back to slide mode here. So there are a couple of things to notice about waves in our everyday experience. We've all thrown a rock into a pond and seen the waves spread out in circles. And we've all been to the ocean, at least I presume everybody here has been to the ocean and seen waves crashing on shore. And the interesting thing about those waves is that they don't seem to move in circles. They move perpendicular to the shore, and they're not circular, they come in lines. So you can say that this kind of a wave has a particular, exists, or at least starts out, in a particular place, but doesn't move in any particular direction. It moves out in all directions at the same time. And this kind of wave is moving in a particular direction, but it's not in any particular place. It's spread out over a wide area. And the question is it possible to make a wave that does both, that is in a particular place and also moves in a particular direction? And the answer to that is no, you can't. And the reason you can't is because it turns out all waves actually move this way in circles. And these waves that come up on the shore in lines are actually a special case of that, where what you really have is a bunch of circular waves. It's like as if you threw a bunch of rocks in the water all in a line, or a big log or something. That's how you make a wave that goes in a particular direction. You have to start out with something wide. And it turns out that the mathematical description of that is a bunch of circular waves that add up and cancel each other out in exactly such a way that they make a wave that moves in one direction but is very wide. So this is called the Heisenberg uncertainty principle. You've sometimes heard about this. It's not something that physicists just pulled out of thin air. It is a fundamental characteristic of the mathematical description of reality. You cannot get away from it. If reality is described by this equation that describes waves, that describes things moving in circles, it is physically impossible to have a wave that is both in a particular place and moving in a particular direction. It has to be one or the other. You can have different combinations of the two. So you can take a wave that's moving in a particular direction, like over here on the left you have a wave moving from left to right, and you can try to narrow it down by putting a barrier in its place, for example. But the narrower you make that barrier, the more that wave is then going to start spreading out. Because if you think about it, what's happening here in the case of a very narrow slit, these disturbances in the water, by the time they get to here, if you have barriers that block all of the water's movement, and what you have here is essentially the same as if you'd thrown a rock into the water at that point. And at that point, you get a circular wave again. So there is no way to get around that. And that is the reason for one of the big mysteries of quantum mechanics, because we live in a world that seems to be made of things that exist in particular places at particular times. Like, you and me and this computer, we can see them. This computer is right here, right now, and it has a particular velocity. Right now that velocity is 0, but if I were to move it across the room, you would be able to say that this computer is in this particular place and it's moving in that particular direction, which would seem to be at odds with what I just told you, that it's impossible to have a wave that is moving in a particular place and moving in a particular direction. You would think that that would also be true of the parts of this computer. So if I took like a keycap off this computer, that would also still be true. That keycap would be in a particular place at a particular time. And if I kept dividing it down smaller and smaller and smaller, that I would eventually get to some fundamental particle that acted like a beach ball, that it was in a particular place in a particular time, and we could trace its movements. And also, there's no such thing as a negative beach ball. There's no way that beach balls can cancel each other out. There's no such thing as an anti-computer that I can put with this computer and have it just disappear. Waves, on the other hand, they can have either a definite position or a definite velocity, but not both at the same time. And they can overlap, they can exist at the same place at the same time, and you can have negative parts of a wave that cancel out other parts of waves and get this negative interference. So it would seem logically that things would have to be one or the other, they cannot possibly be both, right? Well, unfortunately, experiments show that our world, the things that make up our world are actually both. So there is this classic experiment called the two-slit experiment, where you send, it was first done with light. You send light through two slits. So light is an electromagnetic wave. It travels in a particular direction. I wish I could show this to you. I had a laser pointer that I was going to show it to you. It seems like the dot that comes out of a laser pointer is pretty narrow, but relative to the wavelength of the light, it's very wide. So, and if you try to narrow it down, it starts to spread out. So you run it through two narrow slits, and you get circular waves that then cancel each other out in certain places, and you get these dark patches in the pattern of light that ends up on the screen. So that is evidence that light is a wave. But then you turn the intensity of the light down to make it very dim, and you put a very sensitive detector here, and what you get is that the light arrives in little packets called quanta, or photons, and that you never ever get, and that they show up in particular places. So this is why if you take a photograph in low light, it'll come out to be grainy, because what happens in a photographic film is that the photons hit molecules, photosensitive molecules in the film, and they only hit in particular places. And if you don't have very much light, then you can see the actual individual spots where the photons hit. So here's a picture of that. These particular images were generated by the exact same experiment done on electrons rather than photons, but the results look the same. So the photons start to hit in random places, and over time you build up this interference pattern with these dark bands. But every one of these particles arrives at the screen at a very discrete time, and there's a long time between them too. So the light and the electrons, they're both acting like particles and waves at the same time. Well, not quite at the same time. They're acting like waves when they go through the slits, and they're acting like particles when they reach the screen. So maybe they really are particles, and we can catch them in the act of being particles. We can show that they're particles by figuring out which slit they actually went through, because if they're particles, then they must have gone through one slit or the other, right? So we can do that experiment by adding detectors to the slits. And it turns out that when you do that, anything that you do in order to figure out which slit the particle went through makes the interference pattern go away. So that is the first quintessential quantum mystery. Feynman said this was the only quantum mystery. It turns out that's not true. There are a couple of others. But this is the thing that had physicists scratching their heads over quantum mechanics for about the first 50 years of its history. And this is called the measurement problem. So nature behaves like a wave until you make a measurement, until you actually look at what's going on. All measurements produce particle-like results, but the theory says nothing about what a measurement is. The theory is only this equation that describes these waves. And the way that the waves connect to the results of measurements is that the size of the arrow at any given point in time, as these arrows are all squiggling around, at any point in space, the size of the arrow tells you the probability that if you make a measurement there, you'll find a particle there. So there's this inherent randomness in quantum mechanics. Let's see, what else did I want to say about this? Yeah, so that is the sum total of the theory. The puzzle now is trying to figure out what reality is actually like, given that we have this mathematical theory that lets us make very accurate predictions. So the theory says you crunch the numbers on these waves, and then you can make predictions about the results of experiments, but only in the aggregate, only probabilistically. So does that mean that nature is actually random under the hood, or is it just a reflection of our ignorance? So I can actually show you a little bit of this in action. Quantum mechanics describes basically two different things. It describes light and it describes electrons. It describes protons and neutrons too, but for our everyday experience, everything that you experience is essentially the interaction of photons and electrons. So photons are electromagnetic waves, and electromagnetic waves are a special case of this wave where the wiggling of the arrows actually does correspond to something physical. And this is where I wish I had bigger props, but this is a piece of Polaroid film. It's the same stuff that is in polarized sunglasses, so you can actually do this experiment yourself. Can everybody see this? So if you look through here, I wish I had, yeah. What you will see is that the light that comes through here is a little bit dimmer than the light that's around it, but not by much. And it turns out that the light coming out of here is exactly half as bright as the light that goes in. And if I take two of these and put them on top of each other, there is essentially no difference in the brightness. So let me stagger these a little bit here. So here you have two thicknesses of this stuff, and here you have only one. But the intensity of the light here is more or less the same, where you have two thicknesses. It's not quite perfect because this is old and has gotten scratched up in my wallet. But now look what happens if I rotate one of these 90 degrees. Oh, that's interesting. So it turns out the light coming out of the screen is polarized. So that's good. So if I hold this up to this light, you can see that the natural light in the room is not polarized. When it comes out of here, it's polarized. It has a directionality to it. And you can measure that directionality with another sheet of this stuff that you rotate either at 0 degrees or 90 degrees. And if you rotate at 180 degrees, you sort of come full circle again. So what that means is that these electromagnetic waves are, you can think of this as they're waving in a particular direction. Let's say call this up and down. And this stuff filters out. The light that's coming in is waving in all different directions. The light that's coming out is waving in a particular direction, say up and down. And if we put another filter in place that filters up and down, then all of the up and down light goes through. But if we turn it 90 degrees so that the filter is now filtering out side-to-side light, then it's all blocked. And this is already pre-polarized for me, so I don't need two of these. I can show it to you with just one sheet.
Wow.
It turns out the way that these screens work is there's actually some of this stuff built into this screen. That's actually how they produce the dark spots. Is they rotate the polarization of the elements that produce the light. There's another cool thing that you can do actually. This is just kind of interesting. I can rotate this polarization. So let's say that the light coming off the screen is polarized vertically, and I'm going to put a horizontal filter in front of it. Then this is a polarization rotating film. If I put that in between here, then the light comes through again. Whoops. This is a double thickness that I have to use in order to make it work. Can everybody see that? If I put it in front, it does nothing. If I put it in between, then the light can get through.
Wait a minute, why does, if you put it in between it?
Because what this stuff does is it takes the light, the vertically polarized light, and it twists it. That's what this particular film does. It's called, one of these is called a quarter wave plate, and you put two of them together, it makes a half wave plate. And that's just physically what this does, is it takes that electromagnetic field and it rotates it 90 degrees like you're turning a steering wheel. But the other thing you can do is you don't have to filter at either 90 degrees or 0 degrees. You can also filter at 45 degrees. And at 45 degrees, some of the light's still getting through. You can see that you can still kind of sort of see some light coming through here, right? This light now that comes through is now being filtered so that it's waving in this diagonal direction. And if I then filter that again in the vertical direction, then some of the light will get through. So what that means is, so here we have vertically polarized light coming out of the screen. I'm filtering it horizontally so nothing's getting through. But if I put a 45-degree filter in between, now again, some light will get through. And it turns out that when you filter at 45 degrees, again, exactly half the light's getting through. Because if we were using unpolarized light to begin with, it doesn't matter how I'm rotating it. The same amount of light's getting through because the light around here is waving in all different directions. And half of it gets through no matter what orientation I'm in. Here it's all vertical, but if I filter at 45 degrees, half of it still gets through. And now it's waving at 45 degrees, and now if I filter it horizontally again, the angle between this and this is again 45 degrees. So again, half of it's going to get through. All right, so now think about this in terms of we turn the light down so that only one photon at a time is coming through. So now we have a photon that gets to one of these filters and it has to decide whether it's going to go through or not. If I have one of these at 45 degrees, then the probability that it's going to go through is exactly 50%. And every time I do that, every time I put another filter at 45 degrees, the odds that it's going to get through are exactly 50%. So imagine now I have a long series of these filters where every time the odds of getting through are 50%. There are now only two possibilities. Either it's really random, or all this information about which way it's going to go is somehow stored in the photon before it started, right? Those are the only two possibilities. It's possible that all that information is stored in the photon, but we can keep doing this forever. And so there has to be an infinite amount of information stored in a single photon in order for nature not to be really random. And so most scientists believe that nature is really random. That's an inherent part of the reality that we live in, is this quantum randomness. So this is an illustration of what's going on in this polarizations. Unpolarized light is wiggling and the arrows are moving in all possible directions. After it goes through a polarization filter, it's only moving one direction. And we can invent some mathematical notation that describes this. So if we have horizontally and vertically polarized light and we put them together, then we end up with, to add these arrows again. This is slightly misleading because polarization the arrows are going in both directions. And so these arrows really should have arrowheads on them at both ends. And so we kind of seem to be adding them the same way we were adding arrows before. And that's a little bit misleading, but just bear with me. So horizontal plus vertical gives you diagonal polarization. And we can call that, we can even put letters to that. So if we call horizontally polarized light, if we designate that H, and vertically polarized light, we designate that V, then H plus V equals diagonally polarized light. And we can subtract them too. So what is H minus V would be an H arrow plus a negative V arrow, which gives you a diagonal arrow going in the other, pointing down instead of up. And that would be diagonal, but we've already used the letter D, so what are we going to use to describe an arrow going in that direction? I'm going to use K because it has this line in the letter that kind of goes in the same direction. So polarized light math ends up looking like this. You can write these mathematical equations that describe the behavior of this experiment that we just did.
Well, it seems like there's the horizontal and vertical that ends up with 0, right? Because if you...
Right. So remember I said that there are some... The math in general does not describe things that are going on in physical space, so the arrows in general do not point in a direction in physical space. They're purely abstract. And that there are some exceptions to this where the arrows kind of sort of point in directions in physical space, but not really. This is one of those situations. So I'm doing a fair amount of hand waving here to get from what the math actually says to the physical situation. And one of the problems with using polarization as an example is that you can't have, there's nothing corresponding to a negative, really to a negative polarization. If I take a polarization filter and I rotate it 180 degrees, or if I take a polarization filter and I rotate it 180 degrees, it's still doing the same thing as it was before. So if you take one of those abstract arrows and you rotate it 180 degrees, you end up with a negative arrow that will cancel something out. This isn't like that. Catch me after the talk. I'm happy to get into the gory details of this. For now, in the interest of time, you're just going to have to take my word for it. But just as light can't have a definite polarization horizontally and vertically, and along diagonal and the other diagonal axis at the same time. It's one or the other, just like position and velocity. So there are all kinds of these physical quantities that have this relationship with each other, where a physical system can have a definite value for one but not the other. It's not just position and velocity. It's polarization along horizontal and diagonal axes. For electrons, it's something called spin. You can have an electron that's spinning in a definite direction in some along either this way or this way or this way, but not more than one at the same time. And that lets you demonstrate interference in ways other than two slits. So this is a gadget, a schematic of a gadget called a Mach-Zehnder interferometer. This is what one really looks like in real life. But what it is there's a beam splitter here that works exactly like one of these, except that it's a mirror. So the light that doesn't go through gets reflected. So you got light that comes through that's polarized in one direction, and light that's reflected that's polarized in a different direction. And then you use mirrors to bring them back together, and another half-silvered mirror to combine them again. And by carefully adjusting the positions of these things, you can do essentially the same thing as in the two-slit experiment, but focus in on just one of those dark lines or one of the light lines and make very precise measurements. Excuse me. And you can do the same thing with electrons using something called a Stern-Gehrlach apparatus, which is some really strong magnets that are shaped like this, and you produce electrons by heating a bunch of silver atoms in an oven, and hot enough that they ionize, the electrons come shooting out here, and they get split up into two beams of electrons with this magnet in exactly the same way that the polarizing beam splitter splits up light. And I'm not showing you this because the details are really important, but just to make it concrete, these are real physical experiments that people have actually done in the lab. But they all boil down conceptually to something very simple, which is that you take a source of some particles and you split them up in two ways, and then you recombine them and you put some detectors at the end, and you either see interference or you don't. And you can do this with light, you can do this with electrons. It turns out you can do it with large molecules. So the record for this kind of experiment was set fairly recently. There's a guy in France who's basically made his career out of doing interference experiments on larger and larger molecules. I think his record right now is a molecule that has 20,000 atoms in it. Really huge. So these interference effects, we haven't quite done it with beach balls yet, but we have yet to find the line, if there's a line where nature transitions between acting like waves and acting like particles, if that's really part of nature, if there's a line of some size beyond which nature is no longer acting like a wave, we haven't found it yet. So this brings me to quantum mystery number 2, which is something called the quantum eraser, because, and I can kind of sort of show you this. So this light is polarized, and so it's polarized in this direction, and because of that, I can tell, let's see. make sure I get this right. Yeah. Okay. So I've got light coming out of the screen that's vertically polarized and light coming out of this film that's horizontally polarized because I've rotated using this rotating film, remember? So, and I can tell which is which using this as a measuring device. Because if I put it here and I can see the light, then I know that it's gone through this film, and if I can't, I know that it hasn't, right? And I can do it this way. Why is it not working that way? Oh, never mind. So, because I can, remember when I said that if you do anything that lets you know which slit a particle went through, it makes the interference go away? I can't show you the interference part, but what this means is that because I've put this here, if you imagine that here and here are two slits, now this lets me tell which slit the particle went through. And if I try to produce interference using those light going through those two things, it won't work. The interference will go away because I can tell which way it went. But I can, so it's tempting to say that the light has made the transition to particle-like behavior after it passed through this rotator, right? Because now I can tell which way it went and it's not going to produce interference. But I can make the interference come back. How do I do that? By using another one of these at 45 degrees. So look here at this place where I can tell the difference, tell whether it's going through here or through here. If I put this at 45 degrees, it should, if I get it just right, this is not going to work. This worked with the large pieces that I have. I'm not sure why this is, oh, I know why it's not working. I have to do it this way.
Bring that to the cocktail party.
Yeah, okay, so, right. I'm putting it in the wrong place. Okay, so here I have which way information. Here I can tell the difference between light that's come out of here and light that's come out of here using this as a measuring device. But if I put this at 45 degrees, I erase that information. Now I can no longer tell. Can everybody see that? Now it's either dark or it's light, but it's the same in both regions. So this erases the information about what direction it went, and it restores the interference pattern. So it's, oops, I lost a piece. And it's the transparent stuff, so it's hard to see. I'll look for it later. This is called a quantum eraser. So it is, there are some ways that you can modify the situation so that you can tell in principle which way the particle went and make the interference go away, but then you can undo that. And so it can't be the case that simply making the interference go away is what causes the onset of particle-like behavior. You can demonstrate experimentally that that's not true. So that leaves open this question of when and where does this transition from this wave-like behavior to particle-like behavior happen? And Erwin Schrödinger came up with this very famous example called Schrödinger's cat. It seems to only happen when we look at something. And I mean literally when the human mind actually becomes aware of something. You can do this thought experiment where you put a cat in a box and in Schrödinger's case there was a device in there that would make one of these quantum measurements and then either kill the cat or not. It's a little bit gruesome. But that's the classic example because apparently Schrödinger didn't like cats. If you do the math, if you crank the math on this, what it says is that just like the particle is in both places at once, or the wave is in both places at once, the cat, because as far as we know it's also a wave, is both alive and dead at the same time until you look. That's what the math says. Now that's clearly, obviously ridiculous, right? And that's, Schrödinger intended that to be ridiculous. He intended that to show that there must be something wrong with quantum mechanics. There must be something that we haven't figured out yet. But nowadays, we've actually produced physical states Not quite on not on things that are not quite as big as cats, but on things that are big enough to see, on micro mechanical systems, on things that are etched on computer chips. You can actually make little cantilevers that vibrate in two different directions at the same time until you look, and then it becomes one or the other. So, so all of this weirdness has been experimentally confirmed at scales that are big enough to see. I just want to mention very briefly the third and what's probably the biggest quantum mystery, which is something called entanglement. If you shine a laser at certain kinds of crystals, one that's usually used is called beta barium borate. The photons get absorbed by the crystal and then re-emitted as two different photons. And in order to conserve energy, the wavelength of the light that's emitted is lower than the wavelength of the light that goes in. So this beta barium borate is usually, it's called pumping. It's pumped with an ultraviolet laser, and what comes out is visible light. And some of the photons come out over here, and some of the photons come over here, and they're different colors in order to conserve energy. One of the most fundamental principles of physics that we've been able to determine is that there are quantities that are conserved, like energy and momentum. You can't create energy and you can't destroy it. So red photons have less energy than blue ones, so if you have a blue photon over here, it's matched by a red photon over here. If you have a red photon over here, it's matched by a blue photon over here. And in the middle here, you get these rings that are made of green photons that are the same color. And the other interesting thing is that if you have a photon that's in this location, its matching photon has to be over here in order to conserve momentum. But photons are waves, and they don't have a particular location until you measure them. And so what that means is that until you measure one of these two, they come out in pairs. Until you measure one of the two, neither one of them has a definite location. But as soon as you measure one of them, they both do. So here again is that experiment described in this abstract way, because you can do this with photons and electrons and atoms, it turns out. So you have pairs of photons that come out, and you split them up in some way, either by position or by polarization. It doesn't really matter. If you measure if you get a detection up here, you will always get a matching detection down there, and vice versa. But until the measurement is made, neither photon actually has a position. It's random. And Einstein called this spooky action at a distance. The particle isn't really at either detector until it's actually measured, whatever that means. So that means that when one aspect of the photon's quantum state is measured, the other photon changes in response, even when the two photons are separated by large distances. So you can send these two photons to opposite sides of the galaxy, and they won't have a position until one or the other is measured, and then the other one then has a position. The problem with that is you have relativity too, and one of the things that relativity says is that there's no such thing as absolute simultaneity when things are separated by large distances. It depends on the point of view of the observer. So if you have two different observers that are moving relative to each other, then one of them is going to say that this photon was measured before that one, and the other one is going to say that that photon was measured before this one, and yet the results will always agree. This was a philosophical debate up until 1964, when a fellow named John Bell realized that you could actually do an experimental test to figure out whether or not there were these hidden variables that I talked about earlier, whether this randomness was really random, whether there really is this spooky action at a distance or not. It turns out that if you, instead of looking for perfect correlations, if you rotate the filters at either end by some angle other than 0 or 90 degrees, that the predictions that are made by quantum mechanics are different than the predictions that you can make from any theory that assigns definite values to these observables. And the blue line is the predictions made by quantum mechanics. The red line is the best that you can do for any classical theory in order to produce these correlations, and you can see that they're different. The difference isn't much, and so you have to do some fairly sensitive experiments. It took 20 years before anybody was actually able to experimentally test this conclusively. That was done in 1988 by a fellow named Alain Aspect. And the results were, the predictions made by quantum mechanics are correct. And so this spooky action at a distance really does happen. And that is the foundational basis for quantum computing, which there's a whole other talk about that, but you'll read about that in the popular press, because it turns out that you can use this phenomena to do useful things, like you can do mathematical calculations using entanglement much faster than you can with classical computers. Vast orders of magnitude of speed up for certain problems, and that's very useful problems. Like one of them is protein folding. Figuring out how the structure of a protein from the sequence of nucleic acids that make it up is one of the great unsolved problems in biology. And it turns out that that problem could potentially be solved if we build a quantum computer that's big enough. We're nowhere near that yet, but it's looking promising. So far, the skeptics have been proven wrong at every turn, so stay tuned. So that's pretty much it. I'm sorry if you found that unsatisfying. You are not alone. It's trying to figure all this out has occupied and continues to occupy some of the finest minds that humanity has ever produced. There are lots of ideas that have been thrown out there, none of which is widely accepted as the right answer. I can tell you just a little bit about them. These interpretations, trying to figure out what this all means, fall into two basic categories. There are so-called ontic interpretations and epistemic interpretations. Ontic interpretations are interpretations about what's really out there, and these fall into three different categories. There's hidden variables theories, of which the most widely known one is the de Broglie-Bohm interpretation. There's the classical collapse interpretation that says that when you make a measurement, the wave function collapses and takes on a particular value and then continues spreading from there. And then there are many worlds interpretations that say that when you do an experiment that can come out in two different ways, that it actually does come out in both of those ways, that the universe splits, which sounds really, really weird. And the first time I heard it, I thought, no, that is just completely insane. It can't possibly be correct. But it turns out that if you look at the details of the math, it's actually less implausible than it sounds at first glance. I'm not going to say it's correct, but it's much more defensible than turns out to be much more defensible than I ever dreamed it could be. Then there are epistemic interpretations, which say we cannot possibly know what's really out there. The best we can do is come up with an operational description that will help us maximize our knowledge and make the most accurate predictions about the things that we observe without ever actually saying anything about what's really out there. These come under names like cubism, which is short for quantum Bayesianism. There's something called the many minds interpretation, which is the epistemic theory, the epistemic counterpart to many worlds. And there's something that I just learned about recently called convivial solipsism, which is, and I know this sounds really weird, but it's the actual card-carrying physicist in France. He's got a paper with real honest-to-God math behind this that says that what's really going on is that nothing actually exists besides you, or in my case, besides me. But that nature, that physics conspires in just such a way to make it appear to me that there are a bunch of other people out there that I can interact with and who all agree on things like that there's a screen here and that there's a computer here. And if you crunch the math, that's actually the way the math actually does support that point of view. And that is the best I can do, I'm afraid, and the best anybody can do in describing quantum mechanics and our current state of what our world is like. That's just the way it is according to all of the experimental evidence. And like I said, no experiment has ever been done that contradicts any of this. So There's quite a bit of room for improvement, and like I said, fame and Nobel Prizes await anybody who figures this out.
Question on the two-slit experiment. You said that if you reduce the intensity of the light, you get individual particles hitting, and if you measure which slit the particle came from, it loses something. What about putting different colors of light through each of the two slits?
Yeah, that's a very good question. So the reason that you need a laser in order to do the experiment is because you have to get the light to recombine in a very precise way in order to see negative interference. You have to get the peaks of the arrows pointing up to exactly correspond to the arrows pointing down. And remember that what these arrows are really describing is something that's spinning around, in the case of light, that you can see many trillions of times a second. And so you have to get this thing to line up very precisely, and the only way to do that easily is to take a source that has only one wavelength in it, and that's something like a laser. You can demonstrate interference with light that has different colors, but it's very difficult because it's much harder to get the waves to line up in the right way in order to be able to observe it.
Could I hire you to balance my checkbook?
I'm afraid that's still above my pay grade. Talk to my wife, though.
Anybody else have a short question with a short answer? Okay, we'll hit Hugh and then we'll stop.
Hi, thank you. If you could comment on about a year and a half ago, it was reported the Chinese shot photons up to a satellite, and it challenged breaking the speed of light, among other things, and that, I don't know if it's entanglement, but being in two places at the same time,
Yeah.
which is, the whole idea of the alternate universe.
Well, let's not get too far ahead of ourselves. The Chinese experiment that you're referring to was an entanglement experiment. Yes. Remember that I said that quantum mechanics predicts that these entanglement correlations are going to persist no matter how far apart the particles are separated. Well, naturally, you want to test that. And up until that experiment, the record for the furthest distance apart that the experiment could be done was a couple of miles with an experimental setup up in the Canary Islands. And the Chinese shattered that record by having a detector on it. I don't remember whether the detector was on the satellite or whether the satellite just reflected the light back to Earth. I'd have to go look that up. But that was, okay, yeah, you're probably right, because the reason for the separation is because you really want the detectors to be far apart, actually far apart from each other, because that's the only way that you can really demonstrate that these relativistic effects are in play and that the entanglement correlations are not being produced by having the two detectors somehow communicating with each other.
I was going to comment, this is not particularly serious, but I was having a discussion with a group of people about weather world programs in someone's computer. And the question is, could you find, how would you detect it? And it struck me that this could do it, this double slit experiment. Someone is fudging the results.
Yeah, so I actually, I gave a talk about a slightly more advanced version of this talk, where I say a little bit more about the relationship between measurement and entanglement and get a little bit deeper into the math. That's also on YouTube. It's a Google Tech Talk. Go search for The Quantum Conspiracy. Disclaimer, there isn't really a conspiracy. That was just a catchy title to get attention. Sorry, remind me what the original question was.
No question there.
I was going to make a point and then it just flitted out of my mind.
Is this evidence that we are...
Oh, yeah, so, right. Computer simulation. At the end of that talk, I argue that the evidence, you can make a case that we are in fact living in a simulation, but it's not the kind of simulation that is imagined in movies like The Matrix, because in The Matrix you can pop out of the simulation and emerge into real reality. If we're a simulation, then we're a quantum simulation. We're running on a quantum computer. But we, which is to say, the things that are engaged in this exchange of information, the thing that is talking and the things that are listening, we're classical. And that goes back to really deep fundamental structures in the math that describes the behavior of us versus the math that describes the behavior of quantum systems. So we cannot pop out into real reality because real reality is quantum and we're not. And we can't become quantum because we would lose an inherent part of what we are. We would lose the ability to think. So, for example, one of the essential physical phenomena that make us who we are is the ability to copy information. In order to be a human, you have to be able to look out at the world and make a copy of some of the information that's out there and store that in your brain. And quantum systems can't do that. If you have a random quantum state, you can't make a copy of it. If you could, you can show that that would let you communicate faster than light, send information faster than light, which would let you send information backwards in time. And again, I know this sounds really weird. It's actually true, and I can get into the technical details of that if you really want me to. That's about another hour to get to that point. But if you're interested, watch the Google Tech Talk, because that gets into all those details.